Welcome everyone here at the second Enerstock Online conference. Indeed, my name is Bert Gysen. I'm the chair of the Energy Storage TCP. But I want to start with just a short recap, because why this online Enerstock conference, why we already have our Enerstock conferences every 3 years. It is for the simple reason that the whole energy system, as you know, is changing at an incredible pace. And we see also that there is a constant need for more, and not only more, but also more accurate information. So we thought at our TCP that it would be good to have some kind of a midterm, a smaller one, an online conference. And so the Enerstock Online conference was born in 2023. Now the focus of this year was already mentioned by Stephanie. It's about flexibility as a key for an affordable, efficient, and also a resilient energy system. But I would also like, of course, to take this opportunity to invite you already to our next Enerstock conference in person, which will take place in Vitoria-Gasteiz in Spain. It's somewhere nearby Bilbao. It's from the 6th to the 8th of October 2027. So it's still 1.5 years to go, but mark it already in your agenda. This was already presented by Stephanie, so I can skip this slide. And then I would go immediately to the challenges we are facing today, because honestly, I'm convinced they are quite huge. We are dealing with what I would call our planetary challenges. It's about climate, fresh water, land use, ocean acidification, new chemical compounds, and so on. And the Stockholm Resilience Institute, they visualize it quite beautifully. And what we see is that in just 20 years, we've come dangerously close to crossing nearly all 9 planetary boundaries. And that, of course, puts quite a lot of pressure on our planet. And beside that, there is also, of course, the changing geopolitical landscape. In Europe, after 80 years of peace, war has returned. And that made us realize quite painfully here in Europe that we need to become also more energy independent. In the meantime, also the race for critical raw materials is heating up. So we are searching for alternatives. We are also searching for smarter recycling methods, all again to become more independent. And all these things, all these factors, they steer the whole energy transition. And that transition is still driven by one main goal, namely defossilizing our energy system. And the transition is built on a renewable-based energy system with electricity at its heart. By now, I think everyone knows that solar and wind, they are intermittent, so they come and they go. So demand needs to follow supply. At the opening of our Enerstock conference in 2024, I mentioned that providing flexibility will be the biggest challenge in the years ahead. So that it will not be orange, but flexibility will be the new black, the new kid on the block. Flexibility for us can be defined as the ability of the integrated energy system to adjust supply and demand to achieve energy balance across all timescales in order to integrate higher shares of renewables. At the right bottom, you see also that ACER, which is the Agency for the Cooperation of Energy Regulators, they predicted already in 2020, 2021, that the need for flexibility will triple already in 2030. And we all know 2030, it's practically tomorrow if you talk about research. So flexibility is key, and there are, of course, multiple ways to create flexibility. You have demand-side management, you have curtailment, you have interconnections, and of course, also storage. Some storage technologies, they are already mature, they are on the market. If you think about hot water tanks, if you think about aquifer thermal energy storage or borrow thermal energy storage, if you look at all the batteries which are on the market today. But nevertheless, there are still a lot of challenges to tackle, like compactness, pricing, charging, discharging capacity, safety aspects, and so on. And also, of course, how about AI, how to integrate it in our Internet of Things, how to create an optimal flexible sector coupling, what's the most optimal market design, and also, of course, what about all the sustainability aspects? So a lot of challenges, and to solve these challenges, we're gonna call, and that are not the Ghostbusters, but it is our TCP on energy storage. And our TCP was established in 1975, so we celebrated our 50th anniversary last year, and we work under the umbrella of the IEA, the International Energy Agency. At the moment, there are more or less around 40 TCPs active on all kinds of different topics: heat pumps, district heating and cooling, fusion, hydrogen, bioenergy, and so on. But all with the goal of enabling a global collaboration. And I believe that we can say that we are the world's largest energy storage network. Currently, within our TCP, there are 22 countries participating, and we have also 5 sponsors. Now, in these participating countries, all the universities, all the RTOs, all the industry can participate in our TCP via our different tasks. So there are hundreds of experts participating in our TCP. Also nice to mention that in 2026, the European Commission will also become a member of our TCP. Now, what's our mission? Our mission is to ensure that energy storage become a strategic element in the energy system of the future, and this by fostering research and development, but also pre-standardization work of energy storage technologies and the integration in the energy system. We also really want to actively disseminate results via our tasks. We also want to include the industry as much as possible. And we promote also a more holistic approach of the energy system, because storage is in the middle of the whole system. It cannot stand on its own. In our TCP, there are at the moment 8 different tasks running. What is a task? You can see a task as a project where different researchers from universities, RTOs, industry, whatever, but from also different member countries. So at least 3 different countries should have to participate. All these researchers, they will cooperate to investigate a certain topic. A task can start up after approval of the proposal at our EXCO meetings and have a runtime of mostly 3 years. Today, we have 4 tasks running, which are more related to what we should call, or would like to call, the energy system itself. The first one is task 41. It is called ECO-INESTO. So it stands for Economic Assessment of Energy Storage. And the goal here is to contribute to a better understanding on how value is created from a certain benefit of an energy storage technology or system, and then how this can be also translated into a business case. Scope is on all energy storage technologies, as you can see, electrical, chemical, thermal, and all the relevant energy storage applications. Our second task is task 42. That's on system flexibility from medium duration energy storage. You can see in the graph, you see 4 discharge durations and also the cost. And here you can see it's what we call very short. It's from seconds to 5 minutes. Short duration, it's about 5 minutes up to 4 hours. Then medium duration, 4 to 200 hours, and then long duration energy storage. Focus, of course, as mentioned in the title, it's on the medium duration. The goal is to achieve clarity on definition and nomenclature, also to review existing large-scale medium duration energy storage plans and the ones which are under development, to explore what technologies are suited to the medium duration energy storage, and also the understanding the relative importance of these medium duration energy storage as a flexibility provision for the future energy system. We want to assess what resources are available, and we want to develop an understanding of the policy and the financial frameworks. The third task is task 45. It's on accelerating the uptake of large thermal energy storage. And the goal here is to provide the framework and the knowledge to enable an accelerated uptake of large thermal energy storage technology by the market. The objectives are a further improvement of numerical simulations to have better tools for design, integration, optimization, to broaden a large thermal energy storage materials database and materials test methods, and setting up a base for future standards and performance checks for these systems. Also, targeted information and training material for decision makers, implementers, and developers. And if we talk about large thermal energy storage, here we talk about storage capacities more than 1 gigawatt hours. The last task, part 1, is task 46. It's a new one. It's on application-oriented energy storage selection. The goal and the main question is, which storage technology offers the best technical and economic solution in the specific application, and how relevant is the identified application storage pair for the energy system. And here, the direction you look at the energy system is crucial. It gives also different solutions. You can look from the supply side, and in the past, it was all fossil fuels, and they provided all we need related to electricity, mobility, thermal energy demand. In the future, renewable energy provides most electricity, so you could conclude that there is only a need for electrical energy storage. But if you look from the other side, from the demand side, you see that we need 50% thermal energy. You need 25 electrical and 25 mobility. So there is a need for a huge variety of solutions. And you also have to take into account distributed and local systems. So the question is, how much energy do we need, at what time and what form? And that brings us back to the main question. We have also today 2 tasks running, which are more technology improvements related. The first one is task 43. It's on standardized use of building mass as a storage for renewables and grid flexibility. Here we cooperate with the EBC TCP. EBC stands for Energy in Buildings and Communities. The goal is to prepare thermal activated buildings mass energy storage for a widespread, standardized, and economically attractive integration. Task 43 is mainly focused on replication and takes also non-technical challenges into account, including policies. The second task is task 44, and that's on power to heat and heat integrated Carnot batteries for a zero carbon industrial heat supply. Goal is twofold: to identify and to assess the role of power to heat and heat integrated Carnot batteries in the energy system, and to strengthen the international visibility of this option and create a common understanding of this potential in industry and policy. To end, we have 2 running tasks on materials and components. First one, task 47, also a new one. It's on components for thermal energy storage. It's a cooperation with the SHC TCP, the Solar Heating and Cooling TCP. Scope here is a design of heat exchangers and also design of reactors, with a focus on small to large storage capacities, small to large power, and up to 500 degrees Celsius. The objective is to bridge the gap between storage materials and implementation. Last, the second task here is task 48. It's on thermal energy storage materials, also in cooperation with the Solar Heating Cooling TCP, and of course also in close cooperation with task 47. Scope is latent heat storage, thermochemical heat storage, and high temperature sensible heat storage. The goal, to support thermal energy storage materials, but also here we are looking how we can make a permanent activity out of this task. So this was a glimpse very quickly of a running task, and you can find more information also from previous tasks, on our website. It's not about tasks, of course. We also put a lot of energy in dissemination. It's one of our mission things. So I already mentioned the Enerstock conferences, but we also have our online seminars. And you can find, they are recorded. You can find them always on YouTube. Of course, we are also active on LinkedIn, and we have our 3 monthly newsletter. So I think I'm perfectly within the 50 minutes. Thank you for listening. I wish you all a very fruitful conference. And I would like to give the floor, or should I say the screen now, up to the next speaker. It's Beatrice Schulz. Thank you.
Many thanks, Bert. Thank you for the overview. I think now everyone knows what the ESTCP is doing. Yeah, and we move on, as you just said, with Beatrice. So exactly, you can now share.
Thank you, Stephanie. So I will now proceed with the second presentation for today, and what I brought is an overview on how the energy storage markets in Germany are evolving, as well as shedding some more light on different technologies and applications of use and regulatory framework, but also like how storage in Germany is part of the overall flexibility portfolio. I'm happy to say that we are one of the sponsors of the Energy Storage TCP, and we see a huge value in this network as the BVES. So the BVES is the Energy Storage Systems Association. We are based in Berlin, in Germany. We are an industrial association open to all kinds of energy storage within the field of electricity, heat, and mobility. We have more than 400 national and international companies within our member base. Also, a lot of research institutes are part of the BVES. What we do is we are a dialogue partner for politics, administration, science, and the publicity. We help to create a better framework for energy storage. So, for example, looking at different policy decisions and also giving some more input into how you could shape these, what are better regulatory decisions with regards to energy storage to make them, to make a good business case within the market. We are also active in some research and development activities. Maybe that's to the BVS. Our members are different kind of companies. So starting from startups, but a lot of mid-sized company up to, large enterprises that are active internationally, as well as, for example, companies from the finance sector, companies that use energy storage from the industry, for example. That is what we are trying to do. And then the companies do everything from product development to then carrying out the projects, planning projects, as well as operating storage systems. And coming back to the question, why is storage key for an energy system? Not only, but especially with renewables being the dominant resource. I brought some figures to illustrate it, maybe even better. So what we have planned in Germany is to have installed renewable capacities until 2040 of around 560 gigawatts. And the renewable sources we have in Germany are dominantly fluctuating. So it's mostly wind and PV. And now looking at the electrical load that we have in the system of around maximum 90 gigawatts at the moment, we see that we somehow need to fix this gap. And we heard also from Bert, it is not possible to only fix it with electrical demand, but also with demand from the heat side, which makes up the dominant part overall. And we see some effects in our system already that it is lacking of flexibility at the moment. So we have more than 10 terawatt hours of curtailment of renewables in 2023. Now it is even more, which amounts to 3 to 5% of the overall renewable portfolio that we are curtailing in Germany. We have increasing hours with negative prices. So the energy market in Germany is constructed in a way that in times of a lot of supply of renewables and not a huge demand, we can see and observe negative energy prices. And at the moment it's more than 500 hours, but the number is increasing from year to year, and we have more and more system costs. So managing the grids, costs for redispatch are growing more and more. So these are some of the effects we are seeing. The interest to build more storage is growing at the moment, but also to see growth in overall flexibilities from the generation side to flatten the overall generation curve, on the grid side to balance the frequency, as well as on the consumer side to supply power, because now going electric for some of the processes for the overall electrification that needs more power to supply for charging of not only personal vehicles, but also large-scale vehicles carrying goods. You need more and more power to supply and serve all these needs. And we have different flexibility options in Germany. So the grid expansion is one of the options you can see. Germany is kind of a good position for that because we are very interconnected within Europe. So that is one of the options, but not all of the options are the same. Like the grid can do the same time fluctuations and then serve internationally, but to do like a day-night shift, for example, or a seasonal shift, it gets more and more difficult. Then we have dispatchable power plants, such as biomass, hydro, but then also we have things like gas-fired plants, for example. So in Germany, we have new plants for gas capacities that in the future might also be served with hydrogen. So these gas plants should be compatible with hydrogen as well, but that is also something that is currently being in the plans. Then another solution would be curtailment and remote control of facilities. Then we have the demand side flexibility, not only for the industry, but the industry is seeing it as the hugest demand flexibility option that can be easily used. So we are talking about like 7.5 gigawatts until 2045 alone from the industrial sector. And then we have storage in all its forms: mechanical, chemical, electrochemical, thermal, to balance supply and demand during periods of surplus or shortage. So these are the overall flexibility options. And now seeing how storage is currently being used in Germany to supply for flexibility. We have batteries. These are mostly systems doing 1 to 2 hours. So if I'm discharging at full power, full capacity, these systems would hold up for 1 to 2 hours. This amounts to more than 25 gigawatt hours, and correspondingly, the same facilities supply 16 or 17 gigawatts in form of batteries. Which kind of batteries? Home storage systems, commercial storage systems, as well as large-scale batteries that are on the system side. These are all operated by, or mostly operated by companies that take part in the energy markets, as well as residential customers. And then we have pumped storage being installed of more than 9 gigawatts. We have it depends on whether we are in winter or summer, also because of tourism, for example. Some of the pump storage sites are used touristically in the summertime. We have somewhere between 74 and 134 gigawatt hours being installed in Germany. And then we have pumped storage systems being installed outside of Germany, but only connected to our grid, which is also a very nice situation. But these are the numbers for the pumped storage. Then hydrogen, small number of facilities, but was one of the major focuses from the last government, for example. And then we have thermal storage being used. Data here is more difficult to attain. We have a huge number of decentralized small heat storage systems. We have sensible storage for district heating of approximately 21 gigawatt hours. And then we have some larger scale thermal storage that can also be used for seasonal storage, but it's not comparably to, for example, what Denmark is doing for these large-scale thermal storage systems like pit storages. We only have some projects of that kind in Germany. And what we do as an association is we look at all the different kinds of storage systems and what they can do. So what are the applications for them? A good comparison that we always use in Germany, but also internationally, is the Swiss Army knife. Germans really like the Swiss Army knives because they have so many functions. And for a good business case, what we see here is very important that you can do different applications at the same time, or at least with the same storage system, because it makes for a better business case usually. And it also depends, like, do I use the storage system behind the meter, so at a customer side, or am I directly connected to the grid and more serving the grid applications? But there are a lot of different applications that the storage system can deliver. And we heard also from Bert before that it's really important that the storage system really fits the application. So one more advertisement for the new task 46, which the BVES is leading. Andreas Hauer is the task manager. And if you are interested in collaborating on this topic, also feel free to contact me. We have the next expert meeting in April in Graz, but it is also possible to join online. And to carrying out this project, we are supported by the Ministry for Economic Affairs and Energy. Looking now at the markets, we have here the residential storage segment. We are now only looking at the batteries. As I've told, we have a lot of decentralized thermal storage as well. We have around 2.2 million battery systems installed in households, mostly in single family homes. This number amounts to nearly 20% of single family houses in Germany. And that's overall around 13.3 gigawatts and 20 gigawatt hours. If you have looked more closely at the numbers of large-scale batteries and pumped storage before, at least in terms of the power, it is kind of similar. At the moment, a lot of these installations are including heat pumps and charging stations for EVs. We have a huge retrofit potential of existing buildings, so that is something that is being tackled now. For multifamily housing, it proves more difficult to install these solutions because you have a different owner structure, for example. Also, some legal difficulties come to do that, but that is like a new topic. But to do a storage system for like multiple houses, for example, that is something that would be really nice from a perspective for economies of scale, but legally and also from the cost side, looking at grid tariffs, that is a difficult one. Looking into the industry, we have around 14,000 projects with batteries. For the other technologies, data is mainly unavailable. But what we see in the industry is a really high complexity because we have all these different factors that you need to take into account, the different energy needs for heat and electricity, for example, the overall possibilities of electrification. We have a lot of different temperature levels for process heat that are being needed, different load profiles. Some have production on site, whether it's being renewable or conventional. And then there's a focus of value creation. So these industries, they want to make money with selling their goods, for example, not specifically looking at how to save money making them. So there needs to be a shift in focus. A lot of things are happening now, but here are some of the industries that are of major interest for the storage industry in Germany at the moment. And then the white elephant in the industry sector really is heating. So in the end, a lot of the industrial energy demand in Germany is process heat, and batteries might not be the perfect solution for that alone. So we have different options looking at the direct electrification, so taking the energy from the grid. And then we have the electrification also taking into account the thermal storage. So thermal storage systems for the industry are the next thing coming. We can see here a project of the company Kraftblock in the Netherlands. It's a German company doing a power-to-heat storage technology for high temperatures. We now see also a project by Energy Nest, which is currently being built in Germany. And then we see a lot of projects with batteries, for example, for depot charging solutions. So that is something to supply the power to charge different cars at the same time, for example, and to charge them fast in time. Looking into the large scale segment, we see a lot of pumped storage and now increasing number of batteries. And especially the battery sector is at the moment the one that is most in the media we see here, because the markets are quite attractive. You have a multi-market approach that you can use. And we have a really large electricity market, the largest one in Europe, with even more growth rates. Technologies are more mature, for example. So that is something where we will see a lot of growth over the next years, if these systems are being able to be connected to the grid, which is one of the difficulties we see at the moment. To have them all being connected to the grid, that is something that is currently being worked on. Here is one of the largest systems now in operation in Germany by the company of EcoStore. It's a lithium-ion battery with more than 100 megawatts. We also see some projects in charging infrastructure for system infrastructure. So here's a battery that can not only deliver the power for charging, but also doing peak shaving, for example, can deliver system services and so on. So maybe to wrap it up now, a lot of projects are now coming in Germany in the battery field, but also now more looking into thermal storage. Some of the reasons are that Germany is now working on a new grid fee structure. So this might shift some focus also for the industry, but also for the large scale segment. Germany is working on a capacity mechanism and market where storage should also be able to take place in. We have a new government that focuses more towards reliability and more conservative technologies, but at the same time, the topic of reliability is something that storage can serve perfectly. So it is also a topic of energy security, energy independence. So storage fits quite well into this focus. We are now seeing a shift in how grid connections should take place. This is also something that we've seen from other countries as well. A shift in renewable funding that might be not as granted anymore in the future. So storage also co-located with renewable production might become more and more important to have a sustainable business case for renewables. So co-located storage is one of the main focuses in this new government and also in the coalition treaty that we see. But in the end, we need storage on all levels, whether it's being bundled or not bundled with generation or usage of energy. And that's it from me. I've seen the sign from you, Stephanie. I hope I'm not too much over time, but thank you for now.
Thank you as well, Beatrice. No, don't worry. I think we can handle it. And I have to apologize. I didn't introduce your affiliation in the beginning. So Beatrice is the head of the Department of Technologies and Markets at the BVES. So you know exactly what you are asking for. Sorry that I did not mention before. Good. So then we can move on to Seamus. You can already share your screen. Seamus is a professor of dynamics at the University of Nottingham in the UK. And I think we can start directly.
Thanks very much indeed, Stephanie. I'm also the leader of a task within the TCP on energy storage, and that task is about medium duration energy storage. And I want to talk to you about something that I believe you will not have heard about, but in fact builds on the very last point that Beatrice made about co-locating storage, but more than co-locating, integrating storage. So my topic today is wind integrated storage, which I will shorten to WIS, and its relevance to Northern Europe. And I'll start off with just a little preface. It is wind that drives the need for storage more than anything else in Northern Europe. So 3 basic facts. Wind power is going to be the primary energy source for us in Northern Europe and probably will provide more than 70% of all primary power. And about 30% of the energy that is generated by wind turbines will not be naturally used directly. So people will not naturally wish to consume that exactly as it's produced. Now, there may be some demand shifting that can be done to match that up, but it won't be natural for them to do that. So 30% of 70% of all of our primary power. And the third key point is that the timescales that are associated with wind power excesses or shortfalls, they all fall into a particular range of times that I refer to as medium duration energy storage. This is an image that was taken from GridWatch just over the weekend, and you can very clearly see there are dips in wind power and it rises back up. We had a very good month in January because of all the storms, but you see the wind doesn't come and go in at 1 hour or 2 hours or 3 hours, and it doesn't stay gone for more than about a week, which is under 200 hours. Now, I'm passionate about medium duration energy storage, which, as I said previously, is storage that can discharge continuously for periods between 4 hours and 200 hours. And I have written a tool with others that enables you to look at a pattern of net demand. That's the difference between energy demand and energy supply in the future. So you look at this pattern and you can decompose it into all of the energy, into the packets of energy that come out in periods of continuous discharge of various different lengths. And this image that you see here is an outcome from that package. And what you see here is that virtually all of the energy that comes out of storage is the area underneath this curve. Virtually all of that energy that will come out of storage in the future will come out in the medium duration range of times, 4 hours to 200 hours in my opinion. And there's a lot going on about medium duration energy storage. I have set up, in conjunction with the Task 42 of the TCP on energy storage, I have set up MDES Alliance, and I encourage everybody who's online to think about joining MDES Alliance, because it's a very important community to try to push forward the interests of the medium duration storage and flexibility, actually, not just storage. And there are some links here to past events going back to 2020. And the most recent of those links relates to an event on January the 19th about policy and markets for medium duration energy storage. Now, interconnection was mentioned by both Bert and Beatrice. Interconnection helps, but actually it is much less of a solution than people imagine it is. And this is quite a complicated table, but I can explain the key parts to you quite easily. The horizontal axis here is how much we overgenerate. So this is overgenerating by 5%, 8%, 11%, all the way up to overgenerating by 20%. In other words, making more electricity per year than the amount that we will consume by a factor of 1.2 at the end here. And then the numbers in the rest of the table are percentages that tell you how much energy would you have not got directly from the wind, would you have had to take out of storage or some other flexibility measure. And I looked at 7 of the windiest countries in Northern Europe here, and I also did a combination of those 7 countries, a linear combination in proportion to how much electricity they each consume. And it's quite useful to compare Great Britain GB with the combination. So if we have 5% overgeneration, then with Great Britain on its own, we would have to take 20.1% out of storage or flexibility of some sort. And if we connected up seamlessly to all of these other 7 countries, we'd still be trying to take out 18.6% out of storage. And it's quite a surprising thing. Great Britain has quite a relatively smooth wind power profile with huge wind resources. Germany has a much lumpier wind power profile, and Belgium has an even lumpier, probably because of a smaller overall area. So they would benefit quite significantly from interconnection. But actually, Great Britain and Ireland benefit a little bit, but not much. So interconnection, useful, but not a complete solution. Now, a key point of what I wanted to tell you is that the technologies that are most suited to storing energy for this medium duration set of ranges are mostly mechanical technologies. And I forgot to say at the beginning, I'm a mechanical engineer, professor of dynamics, but a mechanical engineer with 40 years of experience as a mechanical engineer. And the kinds of technologies we're talking about are pumped hydro, pushing water up a hill, compressing air and storing the air, pumped thermal, so doing a reversible heat pump, heat engine combination. And then there are two more esoteric ones here, liquid air energy storage and reversible liquefaction or evaporation of CO2. And I will mention that flow batteries and iron air batteries are also capable in this MDES space. But I want you to focus on the fact that most of the solutions are mechanical in nature. And then that prompts me to ask an obvious question. If the technologies that are suited for most of the variability that happens with wind power, if those technologies are mechanical in nature, in other words, you charge them up with mechanical power and discharge them, well, please recognize that wind power is a mechanical power form. So does it really make sense to take 30% of all of the rotor power gathered by wind turbine rotors and convert that 3 times? So does it make sense to take mechanical power and turn it into electricity in the wind turbine, and then turn it back into mechanical power to charge up and discharge storage, and then turn it back into electricity? And the answer to that is maybe it makes sense, but maybe there's something better that can be done. And that's the sort of key to why I'm so passionate to explain to people that actually there is a possibility of doing something different. And that different thing is wind integrated storage, where you have the potential to put energy into storage before you make electricity. And that's the key point. It's putting energy into storage before you make electricity. And if you understand electricity systems properly, you realize that this is how electricity systems have always worked. So a little contrast here. This graphic shows you the kind of conventional approach to thinking about wind turbines and the energy system at the moment. We have a wind turbine rotor that gathers power. We may have a gearbox, or we may just make a generator. And out of this comes electrical power. And if we want that electricity directly, we consume it. And if we don't want it directly, we convert it into something else, store it, and bring it back from that something else. And that's not an insignificant, or it will not be an insignificant amount of power. That will be in the order of 25 to 30% of all wind power will go via this route. And there are two main observations that you should see there. First of all, we have to pay for these machines to convert the energy into something you can store and then back again. And secondly, you have to suffer the losses, because every time you convert energy, you lose some of it. So the contrasting arrangement is this arrangement. This is what I call wind integrated storage. You gather the mechanical power in some form that I simply call X here, and it's a storable form. And if you want electricity directly, you convert mechanical, or you convert X into electricity. And if you don't, you pass X through storage and then fetch it out later. Now, as with the previous diagram, there are two paths for energy here. There's the direct path from the wind turbine rotor to electricity. And for WIS systems, that path will be less good than a conventional wind turbine. But there's the second path where you go through storage. And for wind integrated storage systems, this path will be much better than the other arrangement where we simply say the wind turbine made electricity and now we're going to store it when we don't want it. So most people would say, well, we've got wind turbines that work perfectly well already. Could there be an economic case for developing some new machinery? And in my opinion, it's a slam dunk obvious yes. So I'm a little bit UK focused in this presentation, but the UK on its own will spend at least 200 billion pounds more on offshore wind turbines to reach net zero, hopefully by about 2050. And globally, the spend on wind turbines will be in the order of 3 trillion pounds, so probably close to 4 trillion euros. And the market that is addressable by WIS, could be a quarter of that potentially. So in my opinion, yes, there could be an economic case. Now, I'd love to talk at great length about the technology. In fact, there are 5 different ways that I know of that you could implement wind integrated storage. I'm just going to give you the very shortest hint about one of them. So in this case, the wind turbine rotor doesn't drive a generator directly. It in fact drives a kind of gearbox. And the gearbox is formed by having a compressor here that compresses helium gas and an expander at the other side that expands that helium gas. And the combination of the compressor and the expander gives you a gearbox whose ratio you can change. So the expander drives a generator, and the generator can always run at a constant speed. Now, the helium gas is a very strange application here, because the helium gas, even on the low pressure side, will be about 90 bar, so moderately high pressure. And on the high pressure side, it will go up close to 1000 bar, which is very interesting engineering pressure, but certainly well within manageable limits for engineering. So we have a high pressure loop here that's a bit like hydraulics, except that the fluid going around here is a gas. And because it's a gas, when we compress it, it gets hot. And when we expand it, it gets cold, and we have the capability to take out hotness on the hot side or take out coldness on the cold side. And that gives us the ability to put energy into storage or take it back out again. There's no time to explain this very nice animation. I have built one of these machines so far, and built version 1. And version 1 has taught me a number of lessons, not least about complexity. And this is a very complex arrangement, which is not really practical as a first for installation in a wind turbine, but it's established some principles. And I have tested that machine compressing air, not helium, and it works fine, but a bit of simplification is required to make something that you could actually realistically put in a wind turbine. Now, this graph shows you something very fundamental about a contrast between a WIS system, wind integrated storage system, and a normal system. So the WIS graph here is the blue line, and the normal system is the red line. And what it says is, if you only intend to put a small amount of energy through storage, you're over on the left-hand side of the horizontal axis, you're better off with a conventional wind turbine. And if you intend to put a large amount of energy storage, you're better off with a WIS system. So you're over on the right-hand side of this graph here. So it makes it very clear that if these WIS systems ever do get implemented, they should only be implemented for a small fraction of the wind turbine fleet, perhaps 30%. Finally, just a little note about what modeling shows us that this could do for the UK. So I modeled this. There's a link there to a paper I gave in April of last year, so you can follow that link and find that whole paper. But here's the summary set of results. If you were operating a UK system on hydrogen as the only energy storage mechanism, then your average cost per year for that energy system would be 52.6 billion pounds. Probably best to look at pounds per megawatt hour. If you add in compressed air energy storage, you improve matters a little bit, and you save 2.16 billion. If you now say, well, take away the compressed air and add in WIS, you save a little bit more. And finally, if you said, well, add in WIS as well as compressed air, you still save a big chunk of money per year. Okay, I'm just on time. So my conclusion is there is a very compelling case for developing WIS systems for the UK and Ireland and Northern Europe. There are multiple possible ways that you can do that. WinTP is just one. The marginal benefit of blending WIS for UK has a net present value of more than £10 billion. And whiz-enabled wind turbines should only ever comprise perhaps 30 or 35% of a whole fleet. Thank you very much for listening, and here are some useful links that might be relevant.
Thank you very much, Seamus. I think this is a very, I can imagine some people will have questions because there is a lot of novelty in it. So many thanks for it. Okay, so then we can move on to Kim. Kim is an expert in energy storage and secondary rechargeable batteries at the Chungnam National University. I hope I pronounced it right. Okay, so we see the screen, and Kim, the stage is yours. You can start.
Okay, thank you, Stephanie. My name is Kim from South Korea. The Chungnam National University is located in the Daejeon, the southern part of South Korea. So today, my topic is around the all solid state battery. So actually, the battery, lithium-ion battery especially, is so successful in commercialization. One of the hot topic is in lithium-ion battery is all solid state battery. So today presentation focus on how interface control and the affection of performance of all solid state battery interfaces and contact region between different battery materials like electrode and electrolyte. Even when the material good individually, but the poor interfaces can limit the battery performances. And the goal of this talk is explain this interfacial issue in simple and intuitive way. And I will first introduce why interfaces are important in solid-state batteries. Then I will explain why direct interfacial characterization is necessary. And after that, I will introduce microelectrode hour system to analyze interfaces. Finally, I will discuss some results mean the practical energy storage system. As you know well, the solid-state batteries are attracting and promising attention because they are safer and conventional lithium-ion battery. However, replacing the liquid electrolyte with solid introduces new challenges. The most critical challenge is instability at the electrode-electrolyte interface. Understanding controlling of this interface is essential for that. And many batteries fire accidents are related to use of flammable liquid electrolyte overcharging and heat accumulations and easily trigger dangerous reactions. Solid electrolyte are non-flammable, so which make very attractive for safe batteries. However, safety improvement is not enough. The performances remain. Anyway, solid electrolyte allow batteries to operate with improved safety and wide voltage range. This makes promising and high energy density and high power applications. Despite this advantage, solid-state batteries still face serious performance limitations. Most of that originate from the interfacial problems. Interfacial energy density requires advanced electrode materials and a stable electrolyte. High nickel cathode are one of the strategies to improve energy density, but even with the advanced materials, energy density gains are limited by poor interfaces. Therefore, interface optimization is just important material selection. In solid-state battery, lithium ion must pass through the solid interface. This interface strongly influences and ion transport. Even small interfacial defect can significantly reduce battery efficiency. As a result, interfacial properties often dominate overall battery performances. Conventional battery tests measure the performance of the entire cell. This makes it difficult to separate bulk effect from interfacial effect. To truly understand interfacial behavior, we need a localized and direct measurement method. This motivates the use of specialty interfacial characterization techniques like us. So we have adopted as follows. To study interface directly, we simplify the system as much as possible. Instead of the full cell, we focus on a small, well-defined contact area. This approach allows us to isolate the interfacial behavior. The following slide introduces the microelectrode method in this study. As microelectrode is very small electrode used to probe the local behavior, by reducing the electrode size, bulk effect can be limited, minimized. This allows us to focus on interfacial resistance and stability. The method is especially useful for studying and solid-state battery interfaces. Lithium azerodite was commonly used as solid electrolyte with high ionic conductivity. It was synthesized by using the solid-state reaction method. Phase impurity is important to ensure the reliable electrochemical performances. This ensures that the observed behavior comes from the interface, not electrolyte degradation. Microcavity was formed to control the contact area between materials. This geometry allows precise interface formation. It improved the reproducibility of interfacial measurement. Microcavity help reduce uncertainty in experimental result. This slide shows how the microcavity structure is applied to solid electrolyte. The goal is to create stable and well-defined solid-solid contact. Such contact is critical for meaningful interfacial evaluation. Poor contact can lead to misleading electrochemical result. In these selections, we focus on interfacial electrochemical behavior. The result highlight how interface affect the resistance in and ionic transport. The discussions emphasize trend rather than the observed value. This trend helps us understand the key interfacial mechanisms. Microcavity electrode allow us to measure leakage current as interface. Leakage current indicate unwanted side reaction. Lower leakage current suggests that the better interfacial stability. This information is important to improving battery performances. This slide highlights the interfacial resistance measurement. Interfacial resistance directly affects battery performance efficiently. Lower resistance allows us lithium ion to move more easily. This improves power capability and energy efficiency also. Here we focus on the lithium ion transport behavior. Efficient ion transport is essential for fast charging and discharging also. Interfaces often act as bottleneck for ion movement. Understanding this effect helps us guideline of interface design. This also shows the typical result from this. And this result demonstrates how interface structure affect performances. Even small changes in contact quality can lead to large performance differences. This highlights the sensitivity of solid-state battery interfaces. Proper interface engineering is therefore very critical. Finally, I want to some conclusion. The key takeaway is that the interface dominates solid-state battery behavior. Bulk material properties alone cannot explain performance limitations. Direct interfacial analysis provide clearly insight. This understanding is essential for next generation batteries, especially for solid-state batteries. So thank you for your attention.
Okay, thank you
Okay.
very much, Kim. I was too slow to open my microphone, sorry. Okay, thank you a lot. So, first of all, thanks to all the speakers. I hope we still have Kim, Beatrice, and Seamus in the chat. Maybe you can open your camera exactly so the people know now to whom they will ask a question. Okay, so if you want to ask a question, you can raise your hand. There's this little button on the lower side because everyone in the audience is on mute. This means you have to give a sign. So you can raise the hand on the little button, or you use the Q&A for asking a question. So
if I may add here a word, so Bert had to leave the meeting, but you're welcome to ask any questions related to the STCP to Stephanie and myself, as we are taking care of the secretary of the STCP. So please feel free to post your questions also related to the STCP.
Okay, we have an unusually quiet Q&A question chat in the moment, but I think now there is no. I think there's nothing.
Now there's one question popping
yes.
up in the Q&A. I can read it. So for the wind integrated storage system, what temperature would you be storing and recovering the heat in the system?
Thanks very much for the question. It's very straightforward. You want to have temperatures that are far away from ambient. So on the hot side, you would have temperatures of 800 Kelvin, almost 600 degrees C. And on the cold side, 128 Kelvin, not quite liquid nitrogen, but getting down there. And by having these very far away from ambient temperatures, it means that you can store a lot of electricity in a small amount of rock, and rock would be the medium for the thermal storage.
Okay, thank you very much. We have a second question for you, so I will just add this one. The other question is, are there significant materials savings with the BVES system, especially considering the scale of build out?
So I believe there are. So fundamentally, it's a pumped thermal energy storage system. You need the same amount of rock that you would, or thermal storage medium, as you would have in a different pumped thermal system. So there's no saving in terms of the thermal storage medium compared to the amount of electricity that you're storing. However, there's a very big saving on power conversion equipment. And in particular, there's potentially the transmission systems here are actually lighter than a direct drive generator and have much less permanent magnet material. So in fact, in all probability, the transmission itself is cheaper than a normal wind turbine transmission, as well as saving you all of the costs for other machines that you need to charge or discharge storage. So for example, if you use pumped hydro energy storage, you have to pay for pumps that drive the water up the hill and turbines that allow the water down the hill and turn it back into electricity. All of that is basically built into the system. It's free.
Okay, thank you. I guess there are quite a lot of advantages coming with this technology. So I'm very curious of the outcome of the task of the project. Thanks a lot. So the next question is, I think quite open, but nevertheless, the question is, I'm working on thermal storage systems in Pakistan. Has anybody worked in this particular region? So I guess it's for all of you. And the second question, I just already asked it, so then we can see how it makes sense. The second part is that considering latent heat storage systems, what is biggest thermal facility in operation? So from which we know. Is paraffin wax a good option for gigawatt hour latent thermal storage, like the capacity, considering the leakage and low thermal conductivity? So this goes quite into detail, but I think for sure the first two. Maybe has any one of you worked in the region of Pakistan? And if so, has any one of you considered latent heat storage as a big facility in your mind? Yeah. So okay, the first, but I guess no one worked in Pakistan. Yeah, Seamus, you raised your hand. Or
I can just a very simple comment here. No, I have done nothing about looking at Pakistan as a region or indeed anywhere local to that. I think it's an interesting question about, is paraffin wax a good option for gigawatt hour level thermal storage? I think when we talk about thermal storage, you have to distinguish between storing heat for the purposes of just using heat directly, in which the TCP is extremely strong, and there are a number of very good projects that are currently underway and have run, and that includes the building integrated thermal storage that Bert mentioned at the start. And paraffin wax is a phase change material that is potentially entirely suited to that. But paraffin wax as a material for storing heat from which you want to reproduce electricity is not viable. It's too low temperature.
Yeah, I think there would be different approaches that could be a little bit more beneficial and economic as well, because paraffin wax is quite expensive for large scale, high temperature. But nevertheless, if the person wants to leave an email address, maybe there can be some exchange, or we can also give some task information. So feel free, if you want to leave your name, we can also get in contact regarding this question for more detail. And so moving on to the next question, we have Geoffrey. It's again for you for the WIS. For the energy system modeling you have shown, did you consider sector coupling, or is it only electricity-based analysis? So this would be the first part.
Geoffrey is completely correct. It was electricity only, and I completely agree with him that you get a great advantage from sector coupling. So the level of advantage that you get from WIS is less good than what I said, because that put a bound which was electricity only. Yes, I think sector coupling is a key part, and we have to look at that very, very much. I think particularly with electrically driven heating systems, we are going to get, in the UK anyway, very large amounts of flexibility associated with being able to store low-grade heat and just charge it up when electricity is relatively inexpensive. And so I certainly think that the bottom end, the shorter duration end of medium duration storage will all be mopped up by thermal storage. I do think, however, that actually is a big chunk of the bracket that won't be mapped up by that. And I must find out more about what has been done in Aalborg University, but I know a little bit about it.
Yes, so I guess the perfect connection here to exchange the details. Many thanks. Okay, so do we have any other questions? Yeah, Christoph.
I would have a question to Beatrice. So, looking at flexibility through energy storage, I was wondering, how is this remunerated in Germany, both at the moment and what is planned or what would be needed in future to better remunerate this flexibility option?
Yes, so asking about the remuneration. So most of the storage systems that are being built in Germany, especially like on the electricity side, these are not funded systems. So there's no specific funding for the smaller systems, the residential systems. There were some fundings, but the overall development is not based on the funding. It's more based on the market. So the business case, for example, is to buy and sell energy through the storage system, as well as for delivering system services. So like primary reserve, secondary reserve, and so on. So like shorter term reserve systems, system services for leveling out the fluctuations. So part of it is doing the arbitrage on the energy markets, and part of it is delivering the system services. So that is how it is remunerated. So for the system services, there's kind of a price that then you get remunerated for delivering these services. That is how it is working. And to better supply at the moment for the large scale batteries, it's not really about the revenues you can get out of the market. They are looking quite nice. It is more how you get closer into contact with the grid. For example, we are talking about regional grid services. So this will also be part of the overall grid fee discussion we have in Germany. The electricity storage systems, they don't pay any grid fees at the moment because they are not really a consumer. They are just storing the energy. But now it is being discussed on how grid fees in the future for storage should look like. It is being discussed in a way that storage should pay some kind of grid fee in the future. And that is something we are working on, that this will be in a way where you can reduce then the grid fees through a certain storage behavior, that it is near to zero, for example. So that is something that could get worse in the future. So we're working towards that it is being done in a good manner, so that the storage operates in a good way, but at the same time gets remunerated for what it is being doing, as it is at the moment. And then for like newer systems and newer technologies, or technologies in a new application where it hasn't been before, we need funding for setting up these projects. So that is something we are also advocating for. So you can get to a scale level where it then makes sense again on a market base. So our way as an association is to set up rules that make the market function in a way that it is functioning very well, and that we don't need funding anymore.
Thank you, Beatrice.
Thank you. So there's a second question, I think directed to you, Beatrice. If not, I'm sure we find a general answer there. The question is from Ari. It's regarding the high, respectively low temperature energy storage. Which industry, for example, chemicals, textile, paper, and so on, have the potential to use thermal storage? If you know, please elaborate. I could name some examples, but I'm sure, Beatrice, you have some here as well.
Well, it depends a lot. Like even in the same industry, for different processes, you need vastly different temperatures. So examples for industries that need really, really high temperatures, 1,000 degrees above, is, for example, the steel industry. And then if you go lower, then you come to things like the textile industry, paper industry, and so on. I do not want to elaborate, but maybe Stephanie, you can give more details. What I can recommend is a matrix looking into different thermal technologies and the industries and the temperature levels being needed by the Energy Institute in Linz. So if possible, I will share the link right now, or not.
Maybe if you find it, or we can share it later.
Yes.
I leave the question open, then we can share later the link and anyone can see it. But yes, I think this is a good start. And the task 46, which was mentioned, shall also make some light on this. So if you want, we can also put you there on the information list. I guess this could be an offer to be up to date. Yes, I hope this is answered so far. Not going too much into detail. So we have one more regarding the WIS system. It's with the rising of temperature, so climate change regarding, Does thermal storage be less efficient for systems like this?
Essentially, no. The WIS system has mechanical losses in it, so it will always operate at a temperature above ambient. And one of the key design limitations is that your top temperature that you can store at has to be limited because of materials. So if you try to contain pressures of, I talked about 1,000 bar. If you try to contain pressures of 1,000 bar at temperatures much hotter than 530 Celsius. 530 Celsius, by the way, is 1,000 Fahrenheit, and the Americans, who make all the rules about pressure vessels at high pressures and temperatures, they start to get nervous about that. So, if the bottom end of your temperature range comes up a little bit, you start to squeeze that a little bit. But trust me, humanity will have been wiped out long before the efficiency of a WIS system will be much concerned about whether 10 degrees more would be no problem for WIS, and we're all dead with 10 degrees more in climate change. So I think it's not an issue.
Okay. Comforting. At least the WIS efficiency is still good. Christoph, please.
Thank you. That keeps me calm. Thanks, Seamus. I would like to ask a question to Kim. So I'm not an expert in this all solid state batteries, but I was wondering on the typical discharge times of these technologies, because we had the presentation of Seamus on this medium duration range. So the all solid state batteries, what would be the discharge times? Is it more comparable to lithium ion or also longer?
Thank you for your question. Actually, so all solid batteries should be comparable with the usual existed lithium-ion battery. Actually, lithium-ion battery is most flourishing commercialization items in energy storage. Actually, lithium-ion and all solid-state battery should be differentiated in the performances like a discharge time or energy density, high capacity something, blah, blah, blah. In addition to that, safety also. I mean, your question, Dr. Christoph, asked me discharging time. It depends on the applications. Up to now, lithium-ion battery is most of flourishing in commercialization. It means that there are very verified diversification in commercialization. The performances also can be controlled with the applications. Long-term, short-term, whatever. That is the final goal of a lithium-ion battery, and also all solid state also. It can be controlled with the applications. Is that enough?
Thank you very much for your answer. Thank you.
Okay. Thank you. I think we have one more question, and maybe then we can wrap up. I think it was the same question. A person just retyped it. Many thanks. So we know who you are and we can stay in touch. Perfect. So the question is also about regarding the WIS. Habib is a PhD student, and he's asking which heat exchanger and thermal storage configuration, so cold and hot test, best enable reversible CO2 liquefaction with minimal irreversibility and pressure drop at the grid scale.
It's a great question. I don't profess to be an expert in that reversible CO2 liquefaction. I'm very good friends with the company Energy Dome and with the guy Paul Smith, who is the sort of chief. Well, he's a senior in the management of Energy Dome anyway. So I'm happy to pass that question on. I don't actually personally know, but I do know that they have got actual plant up and running, and I was told by Paul Smith at the event on January the 19th that they have a report commissioned by EPRI that confirms a round trip efficiency of 70% on a real plant. So that's actually very, very impressive. I'll happily put Habib in touch with Paul Smith on that one.